Hello everyone. Today we're talking about 14.5 similarities, and to get this section kind of motivated and maybe also to start with something kind of silly or fun, I want to start by us watching this video. So it's only 15 seconds. So watch what happens in this video. So you may have seen things like this before. So indeed, that was just a toy car, not a full-sized car. Let's watch that one more time. So what exactly is happening here? Why is it that this was so convincing, right? That it really looked like he was getting into the car here. But then a few seconds later, we learned that that's just a small toy car, something that you could probably carry in your two hands. So there are kind of two phenomena going on here. One is a more visual arts kind of phenomenon known as forced perspective, where the camera kind of is angled in a way to make you believe something that isn't true. But of course, the other thing that makes this work is that this car, the car you see on the screen, it looked like what the actual car would look like if it was huge, right? Like if this was a full-size car, a full-sized car, the dimensions of this little toy car seem to match it exactly from the windows to the tires, etc. This notion is the notion that we're going to try to capture today by talking about similarities. So last time we talked about congruences in 14.3. And the idea was that congruences are characterized by the same shape and same size. So if you've got two objects that are the same shape and the same size, like these two, which was the same example we did last time, we say things like this are congruent. We were more rigorous and said we need to be able to use transformations, but nonetheless, same shape and same size was really one of the main things I wanted you to take away from that section. So that's what congruence means. In contrast, we're going to talk about what it means to be similar. And similar is the same idea as congruence in that you still need to have the same shape, like you do up here, but where they contrast is that congruences expect that you still have the same size, that the two shapes are the same size, they're just rotated or done something differently from each other. But with similarity, we remove that restriction. So while congruence needs both the same shape and the same size, we'd like to now remove that constraint of same size. We'd like to be able to say, maybe I want to have a larger version of the same shape. So in this scenario, this should look pretty similar to this scenario up here. So while these two shapes right here are considered to be congruent, these two are not congruent because I could not just, pick this guy up, move it over here and rotate it and get it to land exactly on top of the other one because the sizes are different. But we can say that they're similar because the definition of similarity doesn't care about that. Okay, so things that look like the same shape but are different sizes, we want those to be similar. Now, I want to explore this word similar more because similar is a loaded term. It already means something in English. It means looks the same. And we have to be careful because in math, we're very specific about what we want words to mean. And so just me telling you same shape, maybe not same size, isn't really enough to be concrete. In particular, this part right here, the same shape part, still may not be too clear because I don't mean these things are the same shape. So these two shapes look similar, right? They look similar in the English word sense. Like you can see you've got this like narrow piece right here and this wider piece right here. But by same shape, I am really saying more than just those pieces are the same. So if I had stretched this out accordingly, this is when I would say they're similar. One just looks like a stretched out version of the other, but when I have something like this, the issue that's going on here is that this shape is like super, super tall in comparison to this shape. But this piece right here is really skinny in comparison to that length. In particular, notice this piece is really skinny in comparison to how tall it is. Meanwhile, this shape is pretty much as wide as it is tall. It's not exactly there, but notice how different these proportions are. This one's really tall and really skinny. This one's like sort of tall and not that skinny. So even though these shapes are coming like these shapes, you could make an argument to me that these do look like the same shape, but that's actually not what I want same shape to mean. I want same shape to be maintaining something about the structure of the shape. And I think this is even easier to see with two squares. So here I have two versions of the same square. So I can make this square really big. And now these two squares are similar because they are the same shape, but not the same size. They're not congruent, right? These two squares are congruent because they are the same shape, same size. I can translate one to get it on top of the other. These are definitely not congruent, but they are similar. Same shape, maybe not same size. That's what similar means. However, you definitely wouldn't say that these two shapes are similar. Unlike above, where you maybe would have misled yourself into, or not misled yourself, just without really knowing what I formally mean yet, you might be willing to believe these are similar. I bet you're not willing to believe these are similar shapes, because this one's a square and this one's a rectangle, and yeah, every square is a rectangle, that's definitely true, but not every rectangle is a square, because rectangles can have really, really long stretched out sides. That's not a property of squares. All sides have to be the same. So what I'm trying to really get you to see here is for two shapes to be similar, I really want to think of one shape as the scaled version of the other, but I need to be careful about what I mean by scaled. So more formally, two objects are similar if one is a scaled version of the other, and when I say scaled, I really do mean in every direction. Okay, so up here, oh, don't know how that became red out of nowhere. So up here, these two shapes are not similar because they haven't been scaled the same way. Oh, and that's maybe something I should say. A scaled version in every direction um, by the same amount, right? So turning a square into a rectangle isn't good because it's now like really, really wide in comparison to how tall it is. And I think something that will really help make what I mean here clear is by looking at an image. So imagine you had a picture and you wanted to turn it into a poster. You want to scale it up, but and you probably have done this, maybe not with like a picture and a poster, but maybe you had a smaller version of a picture and you wanted a slightly bigger one. Like think of maybe like a high school graduation photo or something like that. You want to be careful with how you scale it, right? Because if you don't scale properly, the picture might come out looking distorted. And so let's say I wanted to scale an image by 2. what I really mean to scale a picture by 2 is that I have to double the length and the width. And so to demonstrate this example, I have a fun little photo here of a good looking cat. So the idea here is that, maybe I started off with this tiny version, and maybe the dimensions of this tiny version is a 1 inch by 2.5 inch picture. And if I want to scale this picture correctly, I've got to double the width and I've got to double the length. And you can see that you can see just by the numbers that that's what I am trying to convince you I did. Obviously, you have to kind of believe that I did that correctly. Maybe to just be a little convincing, notice let me bring this forward. If you look at this, it looks like it's about this picture is about half the height and about half the width, approximately. I can't be exact on here, but I think I'm just trying to make the point there. So let me just fix this guy right there. There we go. So if I had given you the picture and it looked something more like this, right? You would probably tell me that we did not scale this picture correctly without really looking too hard at it. What is it what makes it so obvious though? In your brain is really good at detecting things like patterns and proportions and stuff, and we can kind of see that this cat's face is basically as wide as it is tall, right? Almost the same. It's kind of like a very round face. But this face is like really skinny in comparison to how tall it is. And of course, the reason that happened is this picture right here is only stretched vertically in comparison to the other picture. So of course, any horizontal distance is the same and every vertical distance got stretched out. So we would not say these two pictures are like scaled versions of each other because they haven't been scaled correctly. And that's really the intuition behind this version of the definition of similarity. Is I really mean when I scale something that I've got to scale it not just in one direction, but in both directions, so that it really looks like I've just blown up the picture. So going back to this first example here, we can now shed some light on this. Yes, these two do look like they're coming from the same original picture. We can see this narrow piece and we can see this wider piece. But the point is that the proportions have to work out. This is really tall in comparison to how wide it is. This one is not tall in comparison to how wide it is. And that's what I mean by similar. So how could we really detect similarity? Here is a distance marker between the two ears of this cat. And now I'm going to copy this and paste it. And notice between this bigger cat's ears, I can fit exactly 2 copies of that same distance marker. So the distance between the cat's ear and the bigger picture is double what it is in the smaller picture. And it works for vertical distances as well. So there is the height of the face. And notice this cat's face is also exactly double the height. So when we're scaling things, it seems like it's we really do mean so what do we really mean when we're scaling things? That's what I want to try to say. This definition up here, when we're saying things are similar if they're scaled versions of each other, how do we detect that besides just measuring some side lengths? What we really mean is that two objects are similar if there is a number k so that the distance between any 2 points is k times as long in the scaled version than in the original. So up here, that number k is 2 because all the distances up here are doubled, right? The distance between the ears are doubled and the height of the face is doubled. All distances are doubled. And notice we also happen to double the dimensions of the height and the width. Did those backwards. So this is the like super formal definition of similarity. It means in the scaled versions, all points are k times as far away as they are in the original picture. And this number k is really capturing how much we scaled the picture by. And so we give k the name scale factor. And as a quick note, this number k has to be the same for the whole picture. Of course, we can't have some parts that are twice as far away and other parts that are 3 times away, because then we would have maybe only scaled. That means we like didn't scale the picture correctly. So it has to be the same. And so we give it the name scale factor. It's called scale factor because it tells us by what factor we scaled the picture. So the key idea to take away from similarity is that same shape, maybe not different size, right? That was kind of what I started with. In other words, proportions have to stay the same. That's really what similarity means. Maybe I make the picture super huge, but as long as the proportions are the same, I still want those to be similar. So keeping the proportions the same is what's going to keep it to be the same shape. And then just saying proportions stay the same means I can make it as big as I want, and that doesn't matter to me. So that's what similarity means. Okay, so now that we have a sense of similarity, how do we use this to, like, where does this come up in real life? How is this useful? So the most common place where something like this happens is really with model cars, model objects. We can use model objects to figure out things about much larger versions without having to build them. So if you want to know how much of a resource you're going to have to use on a big object, you build a scale model first, and the scale model tells you, and as long as it's scaled proportionally, we can figure out a lot of information about the big version without even having it there. So that kind of level of detail, that kind of level of information, that's going to be what the next section is about. This section is just going to be about practicing going back and forth between finding, solving problems using similarity and figuring out relationships between models and the original objects. So that's kind of where we're going and where we are now. So let's just talk about now how to find relationships between models and the original shape, the original objects that the models are based off of. And next time we'll use them to deal with more interesting problems that could be applied to the real world. So consider this problem here. You're looking at a scale model of a car, just like we were in that picture. The model has a length of 10 inches and a height of 2 inches. If the actual car is 200 inches wide, sorry about that, how tall is it? Okay. So in this case, we have our little model car here, and we're given some information about, we know one piece of information about the actual car. And the question is, can we recover the rest of the information? The answer is yes, and it's because of how nicely similarity works. And there are 2 methods to solve this problem. The first method is called the internal factor method. Or I'm sorry, that's the second method. The first method is called the scale factor method. The idea is that we can just find the scale factor directly and use that to find the unknown length, because we know that if we scale a picture by a factor of 2, that means the width is 2 times wider, and so is the height. So by finding the scale factor, we can find that special scale, we can find that special scalar that blows up the car correctly in all directions so that the objects are still similar. Okay, so let's write down what we know. So the car has length 200 inches. The model has length 10 inches. So can we use this to find k? The answer is yes, because if k is the scale factor, remember the scale factor is the special number that tells you how many times larger the new picture is from the old picture. Scrolling back up in this picture, the scale factor was 2 because the dimensions of this picture over here were 2 times the dimensions of this picture. So if k is a scale factor, then what we're saying is that the car has length k times the length of the model car. Here we are using k as our scale factor. So we're literally saying, what is the special number so that the car is, what is the special number that tells us how many times larger the car length is in comparison to the model? And solving for k, we get 20. So this tells us that the real car is 20 times as large as the model. That's telling us what we would have to scale our model by to get the original car, just like how we would scale that first picture by 2 to get the new picture. And so if this is the scale factor, that number is the number that scales all the proportions. Again, in that picture above, we didn't just scale the width by 2, we had to scale the length. So the height of the car has to be the scale factor times the height of the model. But we know now that the scale factor is 20. And so we get that the car is really 40 inches tall. Okay. So that's the scale factor method. What you do is you find a way to find what your scale factor is, and your scale factor gives you the information about the relationship between how many times, by what factor the larger car is larger than the smaller car. It tells you how to scale things. So that's the scale factor method. We also have the internal factor method. And the idea is to compare how two lengths on an object are related. And so if two have some relationship in the original object, then in the scaled version, they have to have that same relationship. So maybe to make this more clear, what I'm saying is, all right, I've got a 5 and a 2 here. Somehow, the way these numbers are related, these two numbers have to be related in a similar way. In particular, notice here, 2.5 inches is 2.5 times 1, and it also happens to be the case that 2.5 times 2 is 5, and that's kind of going to be the idea. Okay. So let's write this out. So the length of the model is 10 inches. And the width of model is 2 inches. So what does this tell us about the relationship between the length and the height? I'm sorry, I wrote width here. This is height. There we go. That makes more sense now. You probably were like, what is he doing? So the length of the model is 10 inches. The height is 2 inches. So what does this tell us? This tells us that the length is 10 over 2, which is 5 times the width of the model. Dang it, height. The reason I keep messing that up is that in my personal notes for myself, I wrote width when I meant height. So I keep copying my notes instead of what's right. All right. What do I do with this? Why is this at all useful? Well, we know that the length of the car is 5 times the height. In other words, in this statement, we kind of get this following relationship that length is 5 times the height. So I'm thinking of L as my length and H as my height. That's what this expression is telling me. And so this works for our model, right? Because it has a height of 2 and 5 times 2 is 10, which is the length of the model. So this gives me like some kind of a internal factor. That 5 is what we're calling the internal factor. It's the internal factor because it's telling us with respect to the model itself, how are its dimensions related? What is the internal factor between them? And in this case, that factor is 5. And so because we get this equation out of it, I guess now the question is, why was that useful? Well, the new car, the bigger version of the car, has to obey this same relationship because the two cars are similar. They're scaled versions of each other. It would be silly if in the big car, the length was not 5 times the height, because then there's no way the two cars are scaled versions of each other. The dimensions have to have that same relationship. And that's exactly what I was alluding to when I went up to that picture up at the top of the page with the cats. And I said, notice that the width, notice that if I multiply the widths by 2.5 on both pictures, I get the corresponding heights. So what this tells us is that since the car has length 200, if I have this equation, I can solve for h. Oops. And I can end up with 40 inches. Now, this is really, really good because notice we also got 40 inches up here, right? 40 inches and 40 inches. So these are just two different methods to find the same answer. So you might be wondering, okay, great, now we have two methods. This is confusing. Why would I want to have two things? Why not just have one method that always works? So, I mean, I don't think I need to really be too convincing about this by now. You guys have seen throughout the semester that there are a lot of ways to do the same problems, and in different contexts, some ways of solving problems are very easy in comparison to others. And that's exactly what I want to show you. So I will specify that usually both methods will work. It's usually not an issue, but sometimes there are cases where one is better, and that's what I really want to demonstrate. So let's solve the following problems using either the scale factor or internal factor method. So first problem, we have a stuffed animal company that wants to make an enlarged version of a bunny. The original has 6 inches by 11 inches, or it's 6 inches wide by 11 inches tall, and the enlarged bunny is 33 inches. How wide should it be? Okay, so spend exactly 2 minutes, pause the video, try to figure out which method is going to help. After 2 minutes, just come back in and we'll finish. Okay, so trying to solve this problem, I think it's helpful to just write down what we have. So original, 6 inches wide, 11 inches tall, and then the enlarged version, we know it's going to be question mark inches wide and 33 inches tall. Okay, so in this scenario, there are two different things we can try. We can try the scale factor method or the internal factor method. So probably, it might depend on how you think about it. For me, the first thing we learned was scale factor method, and I like that one more because it kind of tells us what the scale factor is, right? It tells us how much bigger one is in comparison to the other. So I'm tempted to try the scale factor method, which means I have to compare a dimension of the original and a dimension of the scaled version. And it has to be the same part, right? It can't be a different part. And I can actually see by looking at these two that if K is scale factor, K equals 33 over 11, which is 3. So this is really nice because then that tells us the enlarged version. That tells us exactly how this bunny is scaled. This number right here actually tells us that we're scaling the bunny by a factor of 3. The new bunny is like 3 times as big as the original. So the enlarged version will have as width 6 times 3, 18 inches. Very quick problem to solve once you kind of know this method, right? Cool, good. So that's the usefulness of the scale factor method, is that just gives us immediately how much larger one is than the other. So some of you might have tried to use the internal factor method. You can do that, but if you do it, the internal factor ends up being 11 over 6. And that's a little bit more tedious to deal with. It's not terrible, you can still solve the problem. It's just maybe not really clear how it combines with this one, and it's really easy to make a mistake doing that. Again, you can do it because the internal factor ends up being 11 over 6, and if you multiply that by, or I'm sorry, it actually ends up being 6 over 11. And when you multiply that by 33, you do end up with 18 again, but you might have seen me quibble over whether it's this or that, and that's kind of the quibble that's kind of hard to figure out. And you don't have to worry about that in the scale factor method. All right, here's a new problem. Toy company wants to produce a scaled version of a car. The scale is to be 2.5 inches wide. How long should it be if the original is 6 feet wide and 12 feet long? Okay, once again, pause the video, spend no more than 2 minutes, figure out which method would probably be easier, but as a hint, we just used the scale factor method here, so maybe use the other one first. Okay, as per my hint, we see that the dimensions of the car is 6 by 12 feet. So that means that the car is 12 over 6 equals 2 times as long as it is wide, right? So what do we do with this information? Well, that means the scaled version has length 2 1/2 times 2, which is, of course, 5 feet. Or I'm sorry, 5 inches. One thing that might be really tricky about this is you'll notice that the units are different here and here, right? That one of these has feet and one of these have inches. But the point is that with scale factors, you're just looking to see how much wider. This is what's nice about the internal factor method, is I don't have to dwell on what the units are. It doesn't really matter because I'm just looking to see how much larger one dimension is than another. There's another piece of information that I glossed over when I talked about the internal factor method the first time, which is, why am I doing 12/6 and not, so why not 6/12, right? You should be asking that, like, why is it that one over the other? The point is that what we are looking for is the width of the car. Or sorry, what we have is the width of the model. We're looking for how long it should be. So we need to figure out how the length compares to the width. And the way I've set it up tells us that the car is 2 times as long as the width. Because I put, notice this guy up top, so this is 12 is length, 6 is width. So finding 12/6 says how many times larger the top number, which is length, is than width. Sorry, I'm just writing one letter there for length and width. But that's an important idea that I want to make sure is clear. That's how you decide which one goes on top. If I want to know how many times bigger the length is than the width, I have to do length divided by width, and that tells me how many times larger the top number is than the bottom. That's what division means, right? 6/2 is 3 because 6 is 3 times 2. 12 is 2 times 6. So the length is 2 times the width. And the reason I want to find it like this is because I know the width is 2.5 inches. And so knowing that the length is 2 times the width tells me that I can just multiply that by 2. So there is a small attention to detail when using the internal factor method, and you just have to be a little bit careful. One thing you can do that maybe would help if this is confusing is to set up this following proportional relationship. We can say 12/6 equals question mark over 2.5. And the point is that on the top, we have the lengths, right? We're trying to find the length, and we have the length of the actual car. And on the bottoms, we have the widths. of the model and this car correspondingly. And notice these numbers are the actual car, and these are the scaled versions. Okay. I'm avoiding doing this method overall because this technically uses something from 302, which I am going to talk about towards the end. But for now, I want to punt on it. I want to comment that you could technically use the scalar factor method for this as well, because as long as we're careful and translate the units, we do know the inches and the width. We do know the widths of both numbers, but I do need to convert them to the same units. So 6 times 12 is 72. So the scalar factor is 72, which is 6 times 12, because that's 12 inches in a foot, divided by 2.5. And when you work this out, when you do this division here, you end up with 28.8. And now the point is that the scalar factor times the length of the model is going to be the length of the new. Oh, sorry. We need to be in the same units, right? So we need to do 144 because this is 12 feet in inches. And so length is 144 divided by 28.8. And this magically, but not really, turns out to be 5 inches as well. So you can use the scalar factor method. The issue with it here is that I had to convert the units to be the same thing. I had to convert my 6 feet into 72 inches and my 12 feet into 144 inches in order to use a scalar factor. Okay, so I just want to be clear that you can always use the internal factor method or the scalar factor method. It's just a matter of which one is easier. And I think you probably buy in that the internal factor method makes this one very easy to solve, and the scalar factor is a little more complicated. Okay, just some brief remarks. So just as I just did with the scalar factor method, the units always have to match. You might need to convert things, like on problem 5, in order for everything to work out. You may want to bring everything into a common unit. Again, sometimes units don't matter. When we did this first problem here, when we used the internal factor method, we didn't really care that these things were in feet and that these things were in inches, because we were just looking for how many times bigger one dimension is than the other. So if the length is double the width, then that's true regardless of what units I use. But then when I used the scalar factor method, it really mattered that all my units agreed, because I was trying to deal with everything in inches. I was trying to actually solve for things exactly. I was trying to compare 6. This is really where it happens. I'm trying to compare 6 feet and 2.5 inches. And if I don't change them to the same units, I'm not going to really figure out how many times larger the scaled version is than the original. If I had put a 6 here, it would have been a much smaller scale factor when in fact it's really big. So really, I guess the point is when you're using the scale factor method, the fact that the units match is really important. Also, do include some minor versions of explanations and work just to tell me what you're doing. So stuff like this, just give me some words to tell me, what does this 2 mean? It's how much longer than it is wide, or telling me that I'm finding the scale factor. Just be explicit about what you're doing. And on some of the homework problems, they say something about link the method to a proportion. I actually want to address that now, but I don't want you guys to worry about doing that on the homework. For now, I want to make a quick nod to ratios and 302 as kind of as a closing remark to tie up this section. Okay, let's suppose that for 2 boys, I have 3 girls. And for every 2 boys in my class, I have 3 girls. If I end up with 4 boys, how many girls do I have? Well, if for every 2 boys, I have 3 girls, and if I have 4 boys, the total number should be 6 girls. The reason is that you can think of 4 boys as 2 groups of 2, right? So here are my boys, and they're in 2 groups of 2, and for every 2 boys, I've got 3 girls. And so in total, the number of girls I have is 6. But what really happened here? Notice to go from 2 to 4, I multiply by 2, and to go from 2 to 3, I also multiply by 2. This is exactly like our scale factor. You can think of this as the model, right? The thing that tells us how everything works out. And this is like, I don't want to say the original version, but let's say the scaled version. This is a common problem that comes up in 302 where you have either a recipe or some kind of relationship between two things, and you then multiply by some number to get a larger version to solve these kind of problems where, like, if I have 4 boys, how many girls must I have if this is the model relationship? So in 302, or sorry, let me elaborate on this a little more. So this times 2 here, this is really acting like our scale factor, right? This is telling us if I scale the number of boys by a factor of 2, I better scale the girls by a factor of 2 too, 2 as well. This is like if I had a 2-inch width and a 2-inch height, then this tells me that if I want a 4-inch width, what should the height be if I want things to be similar, if I want them to stay in the same proportions? So this is now a problem that we've seen in this class, right? Like this could be the model car that we have, and this is like how big a new version of the car is going to be, or maybe a new toy. And so in the context of 302, all we're really doing is taking the concept we just talked about today and applying it to like way more situations. Everything we just did is just going to be about talking about, this class is about geometry, right? Geometry is a big part of the real world, and so this tool is really useful to have. But this tool generalizes to scenarios that are still useful to the real world, and they're called ratios and proportions. And you've definitely heard of both of these words. We said the word proportions today informally, and you've definitely heard about ratios at some point in your life. And this right here, the relationship between 2 boys and 3 girls is a ratio. It tells us how 2 quantities are related. That is the exact same thing as me saying my bunny is 6 inches wide and it's 11 inches tall. For every 6 inches that it's wide, it has to be 11 inches tall. In the same sense that if it's 33 inches tall to make the scaled version, I multiplied that by a factor of 3, I better also be scaling that by a factor of 3. I could replace this with boys and that with girls and that with boys and that with girls. And then I would recover something like this problem down here that you've probably thought about before. So what I really wanted to say in all of this is that for those of you that have taken 302 before, know that you've basically already done what we've done today. There's nothing new that you really learned today besides formalizing what we mean by an internal factor and a scale factor. For those of you that haven't taken 302, know that you've just learned a very specific case of something called ratios and proportions. And when you take 302 and you start the class and it starts on ratios, you should think back to this section and be like, oh yeah, ratios is kind of like how two quantities are related together. So I think it's valuable knowing how these things are related and how what you're doing now is going to come up again. And if you've already taken 302, that you're just doing something you've seen before, just in a different way. I think it's valuable making these kind of connections. And since I happen to have already taught 302, it felt worthwhile to share. I'll also point out, a lot of you have probably seen how to solve problems like this in doing something like this. Like you would do 2:3 has 4 question mark, right? And these are the boys, these are the girls, this is the original quantity, this is the new quantity, and you can use a method called cross multiplication to solve this. And I kind of drew something like this way up here somewhere. Oh yeah, I drew it right here as like a brief remark, and I kind of shrugged it off as like, I don't want to dwell on this too much. It's really supported by this proportional relationship. And the thing is that we could talk about it, but the thing is that most people haven't taken 302, and so I don't want to get too caught up in the weeds about the details. I just want you to know that you've probably seen setups like this before and problems like this, and it's going to be connected when you're in 302. Anyways, that's it. That's similarity. The upshot is congruence talks about same shape, same size. How can I get things to land on top of each other? Similarities is a slightly weaker version where you want the same shape, and by same shape, we mean it needs to be proportional to the same original shape. But I don't care about the size. Things can be bigger. All right, that's it for today.